Appreciate the opportunity to talk about this project. A little bit of background quickly on ReLogic Research. We're a small business headquartered in Huntsville, Alabama, and we use finite elements in two ways. Generally, we have what we consider production work, where we use commercial solvers predominantly for product development efforts. And then we have applied research projects where we're typically focused on addressing gaps that our customers have in capabilities, things that aren't offered in the commercial solvers. So that's how I found my way to MFEM. It was through a need for a dynamic topology optimization capability, working with Dan Tortorelli, and got introduced to Boyan. And this project then came along as an opportunity to kind of continue to work with MFEM and try to contribute to the community. So this project Minerva, the goal of this project is to try to make MFEM accessible to a broader base of users, folks that may not be researchers, but maybe designers, folks that already use a commercial finite element software, and provide it to them in a cloud platform. So try to make HPC finite element research and application development accessible to a large group of people. And we're hoping that through collaboration with government organizations, small businesses, academia, that we can get some early adopters of this platform and help develop an ecosystem that's consistent with the current MFEM ecosystem. So that's the intention of Project Minerva. So the concept behind Minerva is really two things. One is to leverage the current mature, commercially available finite element pre-post software to make MFEM models, mesh them, put loads, boundary conditions, assign material properties, and then visualize results. So rather than going off and remaking a GUI for MFEM, we're instead trying to make what currently is about 80% of the global finite element market in terms of software compatible with MFEM. So that's one main aspect of the project. So right now we have the ability to use Femap, Abaqus CAE, and Altair Hypermesh to develop MFEM models and then post-process MFEM results. And we're planning to add support for ANSYS and Nastran in future phases of the research, which would give us about 80% of the current global finite element market. And then the other aspect of this project that we're interested in is disrupting the current commercial software and hardware models for HPCF finite element analysis. I think this was touched on in one of the earlier presentations, but the licensing models for the commercial solvers to even use a modest number of CPUs like 32 is really not practical for most organizations. So MFEM provides the ability to really disrupt that paradigm, and this concept is based on that, and then making MFEM easily accessible to a wide range of users to get them hopefully into the MFEM community, and then eventually to start developing and adding to the MFEM code. So currently we have developed a software layer that is based around an Abaqus input file, and it currently supports 3D solid continuum elements, essential BCs, surface loads, both pressures and generalized tractions, and then multiple isotropic material definitions for static linear analysis. So this software layer will take an Abaqus input file that's set up in a way that's documented to translate to MFEM, and it will output a mesh file and what we're calling a model file, but the C++ code to execute the MFEM model. And right now that automatically happens for serial, parallel, and parallel with adaptive mesh refinement, static linear analyses. So one can generate a model using any one of these pre-post software tools and output the Abaqus input file, and then the software layer converts that to the two files required to run MFEM. And then on the back end of it, we have a database translator. So that takes the VTK output from MFEM and converts it into an Abaqus open results file and an Abaqus proprietary output database file. Between these two files, you can bring results into all of the pre-post software for visualization that I previously discussed. And right now, post-processing currently supports all the elements that are supported by the translation layer, and then displacements, stress and strain tensors, and we're continue to build on that. So here's some examples showing the software layer in action. First thing we did was just recreated the MFEM example 2, simple cantilever beam problem. What we're showing on the right is the model set up in Abaqus CAE, upper right, and then on the lower right is the corresponding results from MFEM, then converted to an Abaqus ODB and brought back into Abaqus CAE for visualization and post-processing. So all the model development and post-processing happens in the Abaqus CAE environment, and the software layer simply translates that information into MFEM files, and then MFEM does the solve. Other examples, just to show the software layer sort of set up arbitrarily, or it's generalized for multi-materials and multi-loads. We have a simple bar with 3 different materials and 2 load cases, and we're just showing also the adaptive mesh refinement that wasn't particularly dialed in for anything meaningful, so it's just kind of refining in areas where you would expect to see stress concentrations. And then the corresponding results there in pair view. I apologize, in the lower right, I wanted to also show the results in Femap, but I forgot to update my build of MFEM this morning to deal with a VTK bug, so I was unable to do that, so apologies there. And then just another example of a sort of complex part. This was something that took about 5 minutes to do. Brought the CAD in, put some loads, boundary conditions on it, threw a simple mesh on it, and then ran it through MFEM. And again, those results are in VTK, but had I updated my version of MFEM, it could have been brought back into any one of those post-processors. So in addition to these, the software layer bringing in these pre-post processor capabilities for MFEM, we also are taking on some MFEM enhancements that hopefully are going to make their way into the next release of the code. We've added the ability to get stress and strain data for VTK output. Also helped correct a bug with ASCII output to VTK as opposed to binary. We're working on both local and non-local elastoplastic material models. Currently working on explicit integration, and then we'll finish up with the implicit integration. We're also adding some support for different materials in MFEM, obviously elastic plastic, but also orthotropic materials to analyze composites, and then also going to work through some simple linear thermoelasticity, so some sort of temperature field, and then CTs to get thermal stresses, and then finally some distributed load cases, so complex pressure or traction distributions on surfaces, and all those enhancements will be open and in the code, hopefully. A little bit more detail on the non-local plasticity model. This is something I'm personally really excited about. This is a kind of a difference maker. It's not something that's commercially available in the production codes, but it's something that we're always asked about by our customers. And this formulation that we're working on is nice in the sense that it introduces a length scale, which then we can directly relate back to fracture criteria for structural analysis. So desirable feature. Really excited to see this implemented, start using it, and bring this capability to some of our customers. The final thing that we've been focused on, besides the pre-post processors and some of the enhancements, is also just demonstrating scaling and setting up a cloud-based platform. So right now, AWS has been the main focus, and we just completed a scaling study on five different virtual machines. Of particular interest to us was the ARM machines, and we were going into this kind of knowing that the 86X architectures, because of their multi-threading, probably wouldn't scale as well. So we did this testing on this example problem with 7.2 million degrees of freedom, and we're in the process of hopefully next week repeating the testing out and up to 256 cores. But in terms of results, as expected, MFEM scales very well up to 64. We're showing notionally there's kind of a triple dot dash curve with the expected performance of commercial solvers. We sort of know they don't scale as well. So kind of one of the many value propositions for MFEM. You can see the 86X architectures roll over due to multi-threading, and as we kind of expected, the ARM architecture provides the best performance, which is interesting then when we look at costs, because the ARM processor, the Graviton 3 in particular, is also the cheapest. So that's a pretty interesting value proposition, just especially when you think about the current software licensing models for commercial solvers, where you basically have to pay for each additional CPU you want to use, and they don't scale as efficiently. So, and in addition to that, we're not aware of any commercial solvers that will run on the ARM architecture. So really sort of interesting and, to me, exciting aspects of MFEM and things that we're really interested in pursuing and kind of making folks aware of, and hopefully attracting them to not only do research in MFEM, but start to use it in an application-oriented sense and do design type work. So the end product of this effort, Minerva, it's obviously based on MFEM, and all future enhancements to MFEM through this project will remain open source. The aspects of the Minerva project that are considered commercial is this eventual turnkey cloud-based platform. Obviously, we know that MFEM can be distributed in a cloud platform now, and that'll be part of what goes on later today, but this is more geared towards a turnkey kind of making it extremely simple for entry-level customers, and then bundling that with the transition layer to allow commercial pre-post software. We're also working on some enhanced documentation, really allowing people. There was some comments, I think, in some of the earlier presentations about some things that would be useful in terms of simpler documentation. So we're really taking that approach to have basic problems laid out, example problems, how to use the translation layer, benchmarking example problems. Obviously, the potential for consulting services around this platform, and then another aspect of the product that I think might be really interesting, especially to some folks on this call, is eventually we hope that it becomes a marketplace for other researchers to commercialize their MFEM-based applications. So if you're developing or building out a capability based on MFEM, you might be interested in Minerva as a place to then make that broadly available to folks and potentially commercialize it. So next steps for this project, we're going to be completing the phase 1 research, those enhancements that I talked about, by the end of the year. And then we're optimistic we'll continue on into a phase 2 where we'll build out the thermal structural analysis capabilities, add things like point loads, rigid bodies, material property distributions, temperature dependent material properties, stuff that most designers use on a day-to-day basis for complex models. And then we're looking to add the electromagnetic support to the integration layer, so being able to bring those pre-post processors to setting up electromagnetics models, and then also adding some fracture mechanics enhancements, things like J integrals and MFEM. As I mentioned earlier, we're going to add support for Nastran and ANSYS pre-post processor software, and then build out that documentation example problems to hopefully get to a beta releasable platform at the end of the project. So this project team is looking for interested parties to eventually beta test some of these capabilities early in our phase 2 program, so towards the middle of next year. So if anyone's interested, please reach out. So that's all I had. Appreciate the opportunity to talk to everyone, and thank you to the MFEM team. And here's our project team from Minerva. Thanks to everyone else.
So I noticed in your, you've got this sort of problem translator, and you're translating sort of down into C++ and having it compile that. Is there a reason you're going with that approach? MFEM's pretty good at doing things dynamically. Is it just the shortest path to victory that you're looking for there? Or?
Yeah, I think we talked about having a much more integrated capability down the road, but right now this is the shortest path to allowing all of these pre-post tools to play nice with MFEM.